Hello Year 10 mathematicians, just going to move on to theoretical probability in the Unit 4 chapter Handling Data. It's the last chapter in the textbook. The main objective today is to work out probabilities from more theoretical experiments. So we're not actually going to conduct any of the experiments or estimate any probabilities. This is where you know the probability in advance and then you state the theoretical outcome rather than doing an experiment. But the one thing which does carry over is a formula which still works, which is the probability of something happening. If you remember from previous lesson, it was, for an experiment, it was the number of successes over the number of trials. And for a theoretical probability, it is the number of successes over the total number of outcomes. So each different experiment or whatever we're going to be doing today, there's going to be some finite number of outcomes, and we're going to be concentrating on just the successful outcomes effectively. So this is a fraction which you've used before, just stating it in a little bit more of a formal fashion. Now this is, I thought I'd mention this just in case, but all of GCSE you don't have to worry about this, but this formula only works for something called equally likely outcomes. Okay, in other words, wherever the outcomes are, they've all got exactly the same chance of happening, because you could manufacture some probability questions where there are different outcomes, but they're not all equally likely. For example, if I was asking the question of whether I was going to win the lottery or not, now me winning the lottery and me not winning the lottery seems like two outcomes, and but the probability of me winning the lottery is not 1 out of 2, because me winning and me not winning are not equally likely. So I couldn't use that fraction to work out the probability of me winning the lottery. But if it was choosing a random card from a pack of playing cards, then each playing card we can safely assume has exactly the same chance of being picked. So then that would work for a playing cards question. So obviously if you were going to do the lottery question, then you would have to consider all of the outcomes, and there are 50 million outcomes for 6 different numbers coming up on the lottery. So if I just chose one of those outcomes, it would be 1 in 50 million rather than 1/2. Now EG number 1 for today is, you've got a fair die, very classical question. So that is rolled. Calculate the probability of a prime number being rolled. So one thing you might want to do is state the outcomes. So a fair die, we assume, is numbered from 1 to 6. Prime number would be a number with exactly 2 factors. The number 1 does not have 2 factors, it has 1 factor, so 1 is not prime. 2 is prime, 3 is prime, 5 is prime. So the probability of rolling a prime number is 3 successful outcomes out of 6 total outcomes. And again, probability is the only area of maths where you don't need to simplify. Probably in the textbook, in the back of the book, they might simplify, but you'll get the marks in an exam for not simplifying. EG number 2, let's imagine now that fair die is rolled 60 times. How many 6s would you expect to roll? So we're not actually going to conduct the experiment, but I've got a fair die. I'm going to roll it 60 times. Before I actually do the rolling, how many 6s should I expect to get? Now, if this was a fair die, which they're claiming it is, 1/6 of the rolls should be a 6. So 1/6 of the 60 rolls, which is 1/6 times 60, which is 10 of them. So 10 rolls should end up being a 6. So that is pretty intuitive. That's what you'd expect to happen. Obviously, if you did conduct the experiment, it's unlikely you will get exactly 10, but that is the definition of random. You can only give predictions. You can never perfectly predict what the future is going to hold. So yes, unfortunately, 10 is the expectation, but not the reality. E.g. number 3, something you've done before or should have done before, is sample space diagram. Draw a sample space diagram to help you list the outcomes when tossing 2 coins. So the way this works is there are 2 coins. So you've got coin 1, and you have coin 2. You draw a diagram and you list the outcomes for coin 1 and coin 2. So it's either head or tail. We never assume it's going to land on its side. Head or a tail. And then inside this diagram, you write the outcomes, which would be head, head, tail, head, head, tail, and tail, tail. And in fact, there are 4 outcomes when tossing 2 coins. 2 heads, 2 tails, and 2 different versions of a head and a tail. That is called a sample space diagram. It is used to list the outcomes of effectively 2 different experiments, or 2 coins, or rolling 2 dice, or whatever it might be. And that's pretty much it. So my only exam tip is, if you can, express probabilities as fractions. You can use decimals, but never use ratios. Never use ratios. If you express a probability as a ratio, you will get 0 marks in an actual exam. You can technically do it, but they don't credit it at all in an exam, unfortunately. So the questions I'd like you to complete today start on page 363, go on to 364. It's just exercise 2. And then move on to exercise 2 star. So it's 2 and 2 star today. And that is pretty much it.